Hi, I'm Mai, and welcome back to Chem Mayhem, where I talk about different chemistry concepts and help you understand them by walking through step-by-step practice problems. In Part A today, we're going to talk about molarity and polarity. Tune in for Part B and Part C. Okay, so in Part 1, we're dealing with this problem. So, we're given these three compounds, and we're supposed to identify and explain which compound will dissolve in water and why. So, to understand and fully do this problem, we have to understand the key concept of polarity. Polarity helps determine the solvability of a substance, and how it does that is it looks at the different types of bonds and the chemical nature of the different solutes, which is the thing that is being dissolved, and the solvent, which is doing the dissolving. So, an easy way to understand it is like dissolves like. What I mean by this is, the same chemical natures and compounds will dissolve with one another if they're the same. Like polar solvents will dissolve with other polar substances, and non-polar solvents will dissolve with non-polar substances. For instance, water and oil won't be soluble because their chemical makeup is different, and with water being polar and oil being non-polar. Thus, if we wanted to dissolve water in something, we would add NaCl, for example, because NaCl is a polar solute and water is a solar solvent. Thus, like dissolves like. So, how do we determine if something is ionic, polar, or nonpolar? Well, to determine that, we have to first draw the Lewis structure and understand the different types of bonds they form. Then calculate the different electronegativity differences as well. And then we can look at the different dipoles. But we should understand the differences between polar and nonpolar. So, polar contains a dipole, nonpolar contains no dipole. Polar can be dissolved in water and nonpolar cannot. These are some of the shapes. The most important part about polar covalent bonds is that the shapes are non-symmetrical and they are uneven. And while nonpolar differs is because it is symmetrical. Ionic is any bonds that is electrons transfer to form ions, while covalent do not. Alright, so starting from the first problem, we have KBr. So, first thing we want to do is we want to look at the different electrons and what we have to work with. So, K, we have one electron. So, I'm going to write that over here. One electron. And then we have Br, which is over here, periodic table. And so we have 7 electrons. So we have 8 to play with. So creating this Lewis structure, we have so that's correct because we have 1, 2, 3, 4, 5, 6, 7, 8. and all have the according amount that they need. So, now what we have to do is we have to look at the electric negativity to determine if it is polar, nonpolar, or ionic. Electric negativity refers to this chart and these values on the periodic table, with fluorine, as you can see, being the most electric negativity, having the most electric negativity, and so on. So we want to write the values in. So K has a value of 0.8, BR has a value of 2.8, and so it will be leaning towards that way, the dipole. And to calculate the electric negativity, we just subtract them. So 2.8 minus 2.8 minus 0.8. So we get 2.0. And according to this chart, when we calculate the electric negativity difference, anything that is 2 or greater is ionic, and anything between 0.4 and 2 going down would be polar, and anything less than 0.4 would be nonpolar. So with our calculations, we have 2, so that means it's polar. And this makes sense because this shape is unsymmetrical because it's leaning towards this way and they are not balanced. Alright, so because it's polar, it means KBr will dissolve in water. Alright, so let's move on to CH3OH. This is a bit harder, but I believe that it's not that true. Alright, so first thing we're going to do, just as last time, we're going to calculate the difference as well. But before we do that, we have to see how many electrons we have to play with. So just going to do this on the side here. So we have 3 of these hydrogens. We have carbon, oxygen, and another hydrogen. So 1, 6, and carbon we have 4, 1. So adding all that together, we have 14. Okay, so draw the structure. Let's go over here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's correct. And I'm going to also draw it this way to help us recognize our shape. So, looking at this, I'm gonna write in the different values using our table, just as before. .5, 3.5, and 2.1. So I see that the pole is all going to the oxygen because it has the most electronegative attraction to it. So go like this, and attractions of the poles will go like that, all circling around the oxygen. Negative. Alright. So now we can calculate our electronegativity. Since we have all these elements, we have to do 2 at a time. So C and H, we have 2.5 minus 0, 2.1, we get 0.4, which is non-polar. However, if we calculate oxygen and hydrogen, we have 3.5 with 2.1. Oh, you guys cannot see. So then we have 1.4. So making it polar according to our chart, since it's less than 2 and around 0.4 and more than 0.4, excuse me. However, so these because it's screwing towards the oxygen, and therefore there is a big dipole. Let me draw that better. It's dipole drawing here. It screws towards oxygen, and there is a net dipole with the negative ending. Therefore, we consider CH3O3 as polar. Alright. Let's move on. Now we have CBr4. Similar to the last one, we're going to calculate how many electrons we have. Carbon, we have 4. Br, we have 4 of those, and there's 7 electrons. So we have 32 electrons in total. So our Lewis structure will look like this. Let's see how many we have. Yeah, our Lewis structure will look like this. Okay, so we have 1, 2, 3, 4, 5, 6, 6, 12, 18, 24, 25, 26, 27, 28, 29, 30, 31, 32. So we have enough electrons and every need of element is met. So now we just have to calculate the electronegativity using our chart here. So we have 2.8 minus 2.5, and so we have 0.3, making it according to our chart, non-polar, because it is less than 0.4. So it's non-polar. And this makes sense as well because our chart here of our Lewis structure and drawing that we did with the bonds, we can see that the shape is symmetrical and they're all balanced, whereas for KBr it's screwed this way, and CH3OH it's all schooled towards oxygen, making these two polar and this one non-polar. Thus, going back to our question, asking us to identify and explain which solutions will dissolve in water, which compound will dissolve in water and why. Our answer would be KBr and as well as CH3OH dissolving in water because they are polar, and because they are polar solutes and will dissolve in water, which is the polar solvent.